Hello and welcome to our virtual Lunch and Learn today. We're going to be talking about Industrial Ethernet 101. My name is Rachel Green and I'm the Digital Communications Specialist here at McNaughton-McKay. And presenting for us today will be Jeff Southern, PLC Product Manager out of our Norcross, Georgia location. Ready to answer your questions out in the comments today is Todd Turnquist, PLC Product Manager also out of Norcross. Feel free to enter your questions in the comments as we go along, and we'll have a Q&A portion at the end for Jeff to answer those in more depth as well. We'll be getting started shortly, but we'd like to allow a few minutes for attendees to join us here. As you come in, let us know where you're tuning in from in the comment section. You can view recordings of previous virtual Lunch and Learns on our YouTube channel under the Virtual Lunch and Learn playlist, and we cover a new topic every Wednesday at noon, so be sure to join us on your lunch break. For anyone just coming in, welcome to our virtual Lunch and Learn today, Industrial Ethernet 101. Let us know where you're joining us from. Feel free to type any questions you have in the comments while our presenter, Jeff, takes us through the basics of Industrial Ethernet. Our specialist, Todd Turnquist, is available to chat with you in the comment section, and Jeff will be available to answer your questions during the Q&A segment at the end of his presentation. If you'd like to reach out afterward, or if you have further questions for Jeff, you can send us an email at macandmaclive@mc-mc.com. Just be sure to let us know which session you attended. And we will have that email address on the screen at the end for you as well. All right, Jeff, we have a number of viewers here with us now, so I will go ahead and pass it over to you.
Okay, thank you, Rachel. This presentation was something I put together at the request of some of our customers. They wanted to learn a little bit more about some of the very basics of Ethernet, and we kind of tailored it around a discussion around industrial Ethernet. So that's why we called it Industrial Ethernet 101. One of the early original developments of Ethernet was actually done by the University of Hawaii because they needed a way to transmit data between the islands. So they didn't typically back then have underwater cables run between the islands necessarily. So they decided to use a radio broadcasting system to transmit data from their mainframe to the other islands in the group. And this is probably the first instance that could be considered an Ethernet-based communication system. It was developed to link to an IBM 360 mainframe. And it's kind of interesting, I thought, because we always kind of thought Ethernet started out on the cable and then switched to wireless, which we use now, Wi-Fi. But actually, it started out pretty much as a radio transmission system. And this is actually why we have half duplex options in Ethernet to start with. Typically, with most radio systems of the era, and this is, we're talking 1970s, they would transmit and then they'd wait for a response after they had transmitted. So that is why half duplex exists in Ethernet today. It also has a big effect on why Ethernet is such a resilient protocol. It has quite long timeouts waiting for a response. Again, electrical interference, and it retries a number of times. So Ethernet is a very resilient network, and this is one of the reasons why the protocol is so resilient, or the design of the system. So if you've ever went into links and you connected to something and you knew it wasn't there and it takes like a minute and a half to give up, this is one of the reasons why. It's actually retrying multiple times to see if it can reconnect to that device. This is also an interesting part of Ethernet, especially as it relates to industrial controls, is that typically an Ethernet network, modern Ethernet network, can survive 80+% failure rates and not have any disruption in the communication that would disrupt the process. So that's kind of interesting. You can be having 80% of your packets not getting to where they want to go on time, but the protocol is so resilient and retries so quickly and so many times that it might work. Now, the problem you get is you might not know that if you're not monitoring the status of the network, and that 85% may cause it to fail. So that's one of the reasons why Ethernet is so resilient, but it's also one of the reasons why we start getting unusual things happening as we don't necessarily monitor how Ethernet is actually healthy at any given time. So Ethernet was formally adopted in the 1970s. It became the IEEE standard 802. So that was in 1985. So all of this happened during the 70s. In the most common access carrier method is carrier sense multiple access with collision detection. So collision detection is actually necessary because, as we said earlier, it started out with half duplex. So you have to be able to detect when two radio transmitters try to transmit at the same time, and then to recover from that. So that's part of the protocol. So it is able to support different types of physical cabling, which, obviously is copper media, fiber, but also wireless. So, and it's able to transmit at various speeds, anywhere from about 10 MIP to 10 gigabit. So that's 2 orders or 4 orders of magnitude that it's improved over the last 20 or 30 years. The layers of Ethernet, this is called the OSI model. Some people call it the Purdue model, but basically it's a layering system of how Ethernet transmits data from point to point or from one to many as a broadcast. It starts out at what we call layer 0, which is really just electrons and photons, either over a copper, fiber, or wireless medium. The official layer 1 is at the binary level. It's media and signals transmitted in binary. One thing that's interesting is that Ethernet works at layer 1 with no MAC address, no IP addresses or anything. It simply transmits to everything. So if you hook 2 devices together over a physical cable, they'll transmit and receive whether they have an IP address or even a MAC address. So the early implementations of Ethernet, they just took the radio signals that we talked about earlier, and they put them on a coaxial cable, and they transmitted down the cable in a radio method. So they literally put radio signals down a cable. So instead of an antenna to antenna, it was just cable to cable, physical connection. But from that, we also get again, it was half duplex. You can't transmit and receive on a single cable at the same time. So that automatically cuts your data rate in half. If you're transmitting at 10 MIP and you've got to do it in half duplex, you really only have 5 MIP of transmission capability between any 2 devices. So the original copper Ethernet that we're more familiar with today, which is twisted pair, when it first came out, there was a thing called a hub, and you plugged all the devices into the hub, and whenever any device transmitted, it sent everything to everything in the hub. So one transmission from one device went to every device in the network, whether you liked it or not. So what they said, well, that's not great. We need some way of limiting the traffic so it only goes between one point, point to point where it needs to go. So that is where they introduced layer 2. Layer 2 adds what they call the MAC address. Every Ethernet device in the world has a unique MAC address. So when you put together a network, the very first thing a switch does is it reads the MAC address of everything that's connected to it and everything that's connected downstream if there's other switches in the network. And this is called the ARP table. So the MAC address basically tells the switch where the packets need to go. So now instead of just having anybody broadcast to everybody, which is obviously quite inefficient, now you have the concept of a MAC address where each physical item on the network has its own unique physical address. And this is not to be confused with the IP address, which comes in at layer 3. Layer 3 basically marries an IP address to a MAC address. And this will become important as we discuss this a little bit later. But just know that a layer 2 switch is truly layer 2. It's not really using the IP address to transmit anything. It's using the MAC address. And the only thing it uses to know where to send stuff related to the IP address is when it builds the ARP table. It asks every device, what's your MAC address? And they say, I'm this. And they say, what's your IP address? And they say, I'm this. So that's how layer 2 transmits. It's actually based on the MAC address, not really the IP address. And that's important because layer 3 introduces the IP address, which basically the difference between the two means that layer 2 is a non-routable message, meaning that it can only transmit to something within its own unique network, whereas the IP address is not tied directly to a physical media or network, meaning that it can be broadcast across many different types of networks. And then we have the layer 4, which is a transport layer. This is where protocols exist. We have data, which is where 2 devices are transmitting data back and forth, and then presentation and application. So basically, when we're working on the plant floor, we're typically working at layers 0 through 3. Layer 4 comes into play when we have things like firewalls and we have, routers and things like that. So layer 4 and above are typically going to be some type of software application. And there are different classes of subnets. A subnet is simply a segmentation of a larger network. That's all it is. And that's really all you really need to know about it, other than the fact that in the industry, you'll hear terms of a Class A subnet, Class B, and Class C. A Class A network uses subnet mask of 255.0.0.0. So they're very large networks. They have thousands and thousands of IP addresses that'll work with that. So typically you're going to see this used by like an internet service provider. A Class B network has a subnet mask of 255.255.0.0, and it'll have, a few thousand different devices on the Class B network, and this would represent typically a large corporate main network, your traditional IT network. A Class C subnet is what we typically use in the industrial controls area because we're dealing with smaller networks. We purposely want to keep them smaller because it has a benefit in performance and resiliency. If you could theoretically run an entire plant with one Class B network. You could just have everything have their own IP address and it's in a flat network. Highly don't recommend you do that. That's actually probably the worst way you could design an industrial Ethernet network, but it is possible. And this brings up probably one of the things I talk about the most when I'm talking to large groups of people about Ethernet is the best thing about Ethernet is most people have a basic understanding of how it works. And that's also the worst thing about Ethernet, because you can get yourself into trouble if you don't understand some of the nuances of why these different class of subnets exist. And traditionally, like I said, we will typically use the subnet mask of 255, 255, and 0. And that has, you can have a maximum of 253 nodes on that network, and we'll discuss why that's true a little bit later. It's also represented by a /24, as you can see on the slide here. It's highlighted in yellow. So it is the network ID is the subnet you're using with the /24. It simply means you're using 24 bits out of 32 to represent that subnet. And that's all it really means. So suppose we want to create a Class C subnet and break the ID of the most typical subnet there is 192.168.1 and 0/24 into 3 equal subnets. The question is, can we do that? And if you look at this chart we have on here, the answer is no. Because of binary math, which is how the subnet is applied, it can only be broken into equal segments that are binary segments of 2. So it's 1, 2, 4, 8, 16, 32, and so on. So we could divide it into 4 equal subnets that would be useful for segmentation and VLANs. And so let's see how that works. We can break any given Class C subnet into 4 equal subnets. Each one will have 64 total IP addresses, and it would have a subnet mask of 255, 255, 255, and 192. Now, for years, when we would talk to people in networks, we would tell them, well, always set the subnet mask 255, 255, 255, and 0. And we would tell them set the gateway address to 000 because nobody really knew what to do with it in industrial controls. The IT guy's been using it for years, but this is something a little more new for OT type guys or guys that work on the plant floor. But we need to start learning how this works. So why would this be of any use to anybody? Why would you just not use 255, 255, 0 as your subnet and always do it for all devices? Well, I'm sure some of you have probably had talks with IT guys and you've asked them for IP addresses for your devices on the plant floor. And you can start getting into situations in larger plants where you're starting to run out of IP addresses. If we wasted, say we have a machine or a line of machines and it uses, let's just make up a number and say 20 IP addresses, we're wasting 253 minus 20. So we're wasting, more than half of the IP addresses that would never be used. By doing this subnetting technique, you can actually break it into smaller chunks and reuse more of those IP addresses and still be able to do routable messages between subnets. And that's kind of the key to what you're doing. You're trying to build VLANs, you're trying to build NATs, you're trying to build other things, and utilize more of those available IP addresses that IT gives you, so they don't have to give you so many different subnets. So that's where this comes into play. The main reason I wanted to show you this is to start understanding why things happen the way they do in Ethernet. So this is kind of the example of breaking a Class C subnet into 4 equal subnets. Each one has a total of 64 IP addresses per subnet with 62 usable host IDs. So why is it only 62 usable host IDs? I just told you that it has IP addresses. And it's because in Ethernet, certain addresses are reserved. The first one being the network ID, which is on the far left. It says it's 192, 168, 1, and 0 is the first chunk of breaking this subnet into multiple, excuse me, breaking this Class C subnet into multiple subnets. So that means the valid range with this /26 mask, or again, 255.255.192, means that you reserve the first one because that's the lowest number in the group, and you reserve the highest one, which is the broadcast ID. You should never, ever, ever set your devices to either the first octet of a subnet or the last. And when I'm talking about that, it means .0 in this case, or .63 for the first one, .64 or .127 for the second one, and so on. And if you do this, this is the problem. It will let you do this, but you will see all kind of weird things start happening in your network as it grows, or even worse, if you try to route stuff, you're going to get some really weird things starting to happen in your network. If you've ever used any of these two addresses in a Class C or Class A or B subnet, and you start seeing really weird routing problems or really weird problems where you maybe use a product like Wireshark to look at the package and you can't quite figure out why they're doing the things they're doing, this might be a good place to look at your network to see if anybody has used one of these network ID or the broadcast ID addresses. So this is important. You need to understand this. And then also traditionally in a subnet, the first usable octet, which in this case on the first line is .1 or .62 is the last one, those should typically be reserved, again, not required, but they should be reserved for your gateway addresses, which we'll talk about in a minute. So typically you're actually limited not to 62, you're really limited to 60 usable IP addresses in this particular case, assuming that you might want at some time to have either one gateway address or possibly even 2 gateway addresses, but typically it would just be 1 on any given subnet. So just keep that in mind when you're starting to understand this. I did this exercise not because you should always run out and break all your Class C subnets into multiple subnets, but just to show you why things work the way they do in Ethernet. And all of this is done, I guess I went back a slide. It's done so that you can do proper network segmentation. So for example, if I set this up this way, then no device in the second network ID can transmit directly to the devices in the first network ID unless you allow it. And you would only allow that using a router or a NAT or some other specific way that you're allowed to allow traffic to jump between one subnet and another. So in this particular case, let's just say that that first subnet ID, the .0, has cameras on it. So I don't want any possibility of those cameras traffic, which is typically heavy network traffic, getting on my controls network. I don't want it mixing with my VFDs. I don't want it mixing with my distributed IO or processor to processor communication. I may do all of that. Say I do all the processor to processor communication on the .64 network. I do all my drives and IO on the .128, and I reserve the 192 for other uses. Maybe that's going to be transmitting to between a SCADA system and this thing. So it's a way of segmenting the data and between subnets, so I don't have any possibility of the traffic accidentally crossing over to a boundary and crossing onto that other additional subnet. So that brings up the topic of why you need to even know this stuff. And this is probably the most important piece. For years, we told everybody to set the gateway address of their network to 0.0.0.0. And the reason we did that is because we didn't know what it was for. I mean, that was typical controls. We just knew it worked if you set it that way. But now with the concept of needing larger networks and more resilient networks and proper segmentation, we need to have the ability to allow data from the outside or the SCADA world or the IT world to cross boundaries and read data from, say, a processor on your process line. And one of the most common ways that's done today, and we'll talk about this a little later, is using a NAT device. Well, one of the requirements of a NAT or even a router is that on any given subnet, it have a gateway address. The way Ethernet works is you receive a packet and he looks at the IP address and he goes, ooh, the response is within my subnet, so I simply do a direct peer-to-peer response to him. Well, what happens if he's not in your subnet? Say he's on, say one of the devices on .64 network is trying to talk to a device on the .0 network here. The guy goes, well, I have no way of sending that to him. He's not in my subnet. So what does he do? He sends the response to the gateway and hopes that the gateway knows how to sort that out. And typically the gateway will. And it would properly send it to the device in the other subnet. So now the gateway address that we've told everybody to set to 000 for years is now important when we start building more modern, more resilient, more segmented LAN networks. So that brings up the importance of segmentation and controls. So we're basically building smaller building blocks, and what they do is they help us minimize network sprawl, build scalable, robust, and future-ready network infrastructure. So we have smaller domain faults. If you plug two cables into a switch, it will cause a layer 2 loop, which is really bad. It'll really cause problems on the network. So if you have everything properly segmented and somebody does that, at least it limits the damage to that one little subnet. You also have smaller broadcast domains. I told you that one IP address is reserved for a broadcast. That is what we're doing now. I'm transmitting data out and multiple people are receiving it. So I'm broadcasting the data with multiple recipients. Well, the good thing about broadcast data is exactly what we're doing now. One person's talking, multiple people are listening. And same thing's true in a SCADA system. Maybe the big computer system up there is pulling the data out of multiple processors or sending data. Here's the time update. That's called a network update manager. You say, here's the current time. Everybody set your clocks. So that's a broadcast message. But broadcast data can cause all kind of problems, because what it does is it turns your beautiful switch at layer 2 back into a layer 1 device. And when the broadcast hits that switch, it sends that packet to everything in the switch. So again, you can cause problems, but if a problem does exist and you've got it properly segmented, you've limited the damage that it does. And you got smaller domains of trust. And there's also some layer 2 devices, structure and hierarchy. I did tell you that when you plug a device into a switch, it has to remember not only the MAC address of the device you plugged in, but let's say it's another switch. It means also any device attached to that switch, which could be any device attached to any port on that switch. So these ARP tables can become quite large. If you don't properly segment your network, you can actually cause some performance. It's minimal, but it is a performance problem, because you have to maintain more and more and more of these ARP tables, and they have to get bigger and bigger, so it takes longer to look up. I mean, this happens at the chip level, so it's very fast. So it typically doesn't cause a problem, but in larger networks, it actually can. It can cause what they call a propagation delay, where this switch took a little bit while to build its ARP table. The next switch took a little bit while to build its ARP table. And so there is some point in the power up sequence where they can't talk to each other because they haven't fully built out this large system in a very large network. Now, again, this happens at the chip level, so it's quite fast, but it can cause performance problems. And you're just adding particular performance problems for no particular reason. So the logical model, means we're going to segment it by geography, or really in a plant, it would be area. A campus model for a network, multi-tiered switch, like say layer 1 and layer 3, where you start doing routing. And the segmentation methods that we use are typical multiple network cards. That's called a bridge. That's the most common and the most secure, because you physically put a bridge and you can put a firewall between those bridges. But the main thing is you have 2 network adapters, one for one network, one for the other. As I talked to you earlier, there's a thing called network address translation. and then local area networks with VLANs. And then you also have VLANs with NAT. So they combine both of the two. And then you have some threat management security appliances that can also provide some segmentation. And we're going to talk about each one of these types. So the first one is a network segmentation with bridging. And it's kind of what you would expect. Okay, the plant network comes down and pulls the processor, but he can't go out another network card and start messing around with devices on that second network. That might be your drives and I/O. So you formed a physical separation between the two. So physical separation is typically what's called a bridge. We also have things called segmented using VLANs, which we'll talk about in a little bit. So you can actually combine the idea of two NIC cards with VLANs, and we'll talk about that in a minute. So the benefit, obviously, is probably one of the most secure ways you can separate things, because you could, in fact, there is a rule in control logics. It will not allow that message from the plant network, in this case, to go down to the controls level network unless you specifically tell it to. It's blocked by default. The challenges are, of course, what happens if you need to see something that's down at that second layer or on the second Ethernet device. You can't do it easily in this type of segmentation. So this has its place, but it also has its limits. In other words, we formed a really good separation, but now you can't see anything. So that's where the concept of using two Ethernet adapters and VLANs or some type of layer 2 routing becomes important. And the next type of appliance is a NAT appliance. A NAT simply has one goal in life. He allows a device on a private network, which we show 3 private subnets or private networks down here, to also have a window or an IP address on a public network. So that's the concept of a NAT. And it basically does exactly what it says. It allows it to have a private IP address and a public IP address. And this has a big advantage in controlled networks. Let's assume that this drawing represented 3 lines that are identical. So they have the same number of drives, the same number of controls, same number of everything. And we would like to have one program for all 3 lines. Well, the problem with that is what happens if the SCADA system from the plant needs to talk to all those? They all have the same IP address. Well, one of the big rules in Ethernet is you can't have 2 devices on the same subnet with the same IP address. So you immediately have a problem here. Well, the NAT solves that problem. It says, well, okay, each one of you can have the exact same 192.168.1 scenario, but in the public world, you'll all 3 have a different IP address. In this case, it might be the processor. Maybe the SCADA package wants to go down and read data from each one of those 3 processors, but it couldn't do it if they were all the same IP address and there was no NAT. It wouldn't be a physical possibility. You couldn't do it with Ethernet. So the NAT allows that to happen. It allows you to have a published IP address and a private IP address. So now the nice thing is I can maintain one program for these 3 processors, and I don't have to have 3 different programs with 3 different IP addresses schemes in. And not too big if you got 3, but what if you got a plant that's got 80 lines and they're all identical? That could be a big problem right off the bat. So in its simplest terms, it allows a network node to have an IP address on its local network and also a different IP address on a larger public network. Without NAT, the internet could not exist. You guys are all listening to me, and I guarantee you that somebody out there's computer has the exact same IP address as the one I'm talking to you from. Because my computer currently has an IP address of 192.168.0. I think it's 54. And somebody out there may have that same address, but only on the private network, not on the public network. When you log into your ISP, the first thing he does is apply a NAT and says, I'm going to give you an IP address of this on the public network, and it allows us to talk together even though our devices actually have the same IP address. So a layer 2 NAT rules, that's the rules of a NAT, is the private IP address and the public IP address must be on different subnets. That goes back to my original analogy of why you might want to break a Class C subnet into multiple subnets. You can't utilize a NAT unless they are different subnets. So a NAT appliance also must have its own individual IP address on both the private and the public network. So the device itself has to have an IP address on the public network. It has to have an IP address on the private network. And then any network node that wants to utilize this NAT to talk to a larger network must have its gateway address set to the IP address of the NAT appliance on the private network. That's important. If you use one of these devices, I'm going to go back a slide. So if you use one of these devices as a NAT, it must have an IP address on the private and public network. And say with this PLC, we have to put the gateway address that we used to tell you to put 0 in there, now has to have the gateway address of that NAT device in order for it to function properly. So that's exactly what happens. The SCADA system says, I want to read this tag value. The processor says, okay, here's the tag value. Oh, wait, you're not in my subnet. I don't know how to send that back to you. So I'm going to send it to the NAT, which is my gateway address. And the NAT hopefully knows how to send it back to the SCADA system so he gets his response. So that's the whole concept of how NAT works. It's called network address translation. It does exactly what it said. It's one of the few devices that its name implies it does what it says. So the subnet mask for all devices to use the NAT function should have the same subnet mask. Otherwise, weird traffic issues can occur. So I just told you that for 20, 30 years of me being in this business, we told everybody to set the subnet mask to 255.255.0. But there were a few smart guys out there that figured out, I can just set that subnet mask to 255.255.0.0, and I can talk across multiple Class C subnets. And it's true, it works just fine. At that point, it becomes a Class B network, but you've still done it. Well, here's the problem. If I mix some devices that have the 255, 255, 255, or the /24 mask with devices that have a larger mask, all kind of weird things will happen. And this is why. Let's just say we've set this up just like it was in this slide, where we're going to use this NAT device. But one of the processors has a subnet mask of 255.255.0.0. That means he can talk to any device that starts with 192.168. It could be .1.254. It would still think it could talk to it. So a device from another network sends it a request. It goes, I got this monster subnet. I can respond directly to this guy. But here's the problem. He doesn't exist on that little subnet. You've told him he's part of a big subnet, but in reality, he's only part of a little segmented subnet because we properly used a NAT device to segment the traffic. He tries a direct response. It just goes nowhere because it doesn't transmit it to the gateway. So there's no way the NAT can send it back to the device that sent the original message. And I've seen this happen dozens of times, and it takes hours to figure this out because you're looking at Wireshark and you're saying, well, I see where SCADA sent the packet requesting the data from the processor, and I see where the processor responded to the packet, but it never went anywhere. It's because its subnet mask was set wrong because somebody did it at some point in time and didn't understand or didn't care at the time, why that might cause a problem in the future. Even if you had the gateway address set right, it still wouldn't work. So it's important that the subnet mask for all devices used in NAT functionality have the correct subnet mask, or in this case, the same subnet mask. And another thing to know about NAT appliances, they can also be layer 3 devices. We don't typically get into that much in controls world, but just be aware that they sometimes combine routing with NAT functions. And these are typically administered by IT departments. So you're probably going to have to work with the IT department if your NAT requires layer 3. In most cases in controls, they don't. It's just a simple layer 2 NAT. So segmentation with VLANs is our next option. So I told you that a NAT is the concept that it has a public address and a private address. And that's it. That's really all it means. But we can also segment VLANs using VLANs. A VLAN is a virtual LAN. That's why the V stands for virtual and LAN stands for local area network. So it's a virtual network. And what it does is it segments a network logically without being restricted by physical connections. And what I mean by this is that typically a switch, anything plugged into that switch, if everything's set the same and there's no VLANs, they can all theoretically talk to one another because they're physically connected. A VLAN can break a simple switch up into multiple switches, and they can't talk. The software in the switch does not allow the traffic to jump from one VLAN to another, regardless of any other IP address setting or gateway setting or subnet setting. It is a physical, well, not physical, it's a software barrier within the switch that breaks that switch effectively into multiple switches. The VLANs also can exist across switches, and we'll talk about that in a second, but just know that a VLAN basically means a virtual network. It basically divides switches into virtual switches that can have completely different communication settings and completely different traffic. One of the great things about this is it within the switch, it restricts unwanted traffic, or more specifically, unwanted broadcast and multicast traffic to cross those VLANs. So we go back to our camera thing. Well, the camera is producing huge amounts of broadcast data, and we don't want it on the Ethernet IP devices network, which is LAN 102 in this. So it provides a physical, it's not physical again, it's a software separation within the switch so the traffic cannot jump across those two ports, physical ports on the switch. And it's software configurable. You can decide which ports exist within any VLAN. So at its basic element, it breaks a switch into multiple switches. And that would be great if you had a network small enough where everything plugged into the same switch. Well, obviously in the real world, that typically doesn't happen. So you have to have a way of routing the VLAN between switches, and that's a layer 2 function. It's called VLAN trunking. And yeah, I didn't make up these words, but that's what it means. It means that one switch can have multiple VLANs on it, another switch can have multiple VLANs on it, and they're the same VLAN. So VLAN 101 on one switch is VLAN 101 on the other. VLAN 102 on that switch is VLAN 102. So it allows you to run a single cable between the switches and allow the VLANs to exist across that single cable. And there's a couple of things you should think about that. So typically your trunking port, the physical port on the switch, is usually the fastest port on a switch. For example, if we use our 5700 switches, we want to route VLANs using the gigabit ports instead of the 100 base T ports. You can set them up either way, but you're doing yourself a disservice because we're taking multiple VLANs and we're going to shove them through that one port to switch. You want to make sure that's the fastest switch that switch is capable, the fastest transmission rate that switch is capable of. So typically your trunking port on your switch is the fastest port, which in our Stratus 5700 line would be the 2 gigabit ports on it. So it is all software manageable. In other words, this is all software settings that make this work. And this is a fun part, little fun fact. If you divide a 5700 switch into 2 VLANs and it doesn't have layer 3 routing capability, the only way you can get data from one switch to another is physically attach a router to 2 of the VLAN ports. In other words, if you got the switch broken into ports, you have to physically connect the cable to a router or it won't work. You'll effectively make it impossible to get traffic from one VLAN to another. Now, most of our switches have some inter-VLAN routing capabilities, which is what they're talking about here. So as I told you, VLAN trunking allows one VLAN on one switch to exist on another switch. Inter-VLAN routing does what I said. It allows one device on a VLAN to talk to another device on a VLAN, assuming you set the rule up to allow that. So most of our Stratix switches, of course, support VLAN trunking and inter-VLAN routing. So it's not a true layer 3. So some people call this 2.5 layer because it can do some basic routing, which is typically limited to a router or layer 3 switch. But they had to add this functionality, or as I said, you would physically have to put 2 cables into that switch and go up to a router to allow the switch to talk to the other half of the switch. And that's kind of what this definition here shows. It shows, I apologize, went the wrong way. So just be aware that inter-VLAN trunking means one switch, VLAN can exist on one or more switches. Inter-VLAN routing allows the 2 VLANs to talk to each other, assuming you want to allow that. So this is pretty important. So a security appliance does a different segmentation, but it's a little different. What it does is it allows secure data to pass through it or not. It doesn't have to be VLANs. It doesn't have to be NAT. It typically is, but it's simply a security appliance that says it's okay for this device to go through me and talk to that device. And these can be so sophisticated, they can block basic traffic. They can say IO traffic's not allowed, but HMI SCADA traffic or HMI traffic is allowed. So that's what a security appliance does. It does proper segmentation using that technique. And this brings us down to the cultural and organizational perspective chart. If you've ever wondered why there typically is often a headbutting between an IT professional and an OT professional, and if you look at their priorities, they're actually reversed. In an IT network, the primary thing is confidentiality or security. And then integrity is always important. And then availability is at the bottom of the list. In other words, if I take the copier out for something I'm doing for 20 seconds, nobody really cares. Nobody probably even notices. But I guarantee you on the OT network, if I take the communication network down for 20 seconds and it starts throwing boxes in the floor, somebody's going to come looking for who did it. So their priorities are the exact opposite of one another. And that gets down to the last line in here. It says the results of a network reliability of 99% of the time. The IT manager gets raised, the OT manager gets fired. If you take the plant network down 1% of the time, you're probably going to kill the productivity of that plant. So this is important to understand as an OT and IT guy, is that where does the conflict come from? It comes from the fact that their priorities are the exact opposite. So availability means that you want that device to be able to talk to the processor, talk to its driver, its IO is the most important thing to you. So this is why they have to work together, and they should work together. But this is where a lot of the conflict comes from. I just wanted people to be aware of why the conflict exists to start with. This is why. And I notice we're running a little bit long here. I'm going to briefly go over device level rings. And what a device level ring is an embedded switch technology that allows us to communicate with a resilient media. In a linear bus here, if I disconnect one of these cables, the devices downstream can no longer communicate. But if I have them in a ring, I can survive one media failure or one device failure and still talk to everything else in the ring. So Rockwell developed this, and it's a specific ring topology because it has the ability to self-heal within 3 milliseconds, which means for up to 50 nodes on a DLR ring, you can self-heal if one of the devices or somebody unplugs one of the cables or a cable gets cut or whatever. And typically the IO is never even disrupted. It never even has a problem. In some ring topologies, which are utilized in other areas of IT in the plant, it could take up to 30 seconds for that ring to heal itself. So you can't take the network down. So this is why a DLR ring is so important in an industrial network for the resiliency of the media. We can connect devices that don't understand the ring protocol to an ETAP. So that just allows an older device to speak on a ring. It's available with copper and fiber ports, so you got long distances involved. There's a NAT. I told you NATs are kind of cool devices. There's a NAT built into one of the ETAPs, so we can do the proper segmentation. Great use of this is compact logic. You build a DLR ring to talk to all the devices, but you need to also have an IP address for the IT network. This guy gives you the IP address to the network because it can map internally the private address of the processor to the public address for the NAT. There's also a specific router built for it. The ETAPs are capable of being a ring supervisor. Any ring protocol must require that the packet gets stopped somewhere around the ring, otherwise it would go around the ring endlessly. So somebody has to be a supervisor. So basically what it does is it broadcasts a beacon around the ring so it'll know how it can detect a broken cable connection or a missing cable connection. And this broadcast is part of the DLR protocol. So it's specific to the DLR protocol. And the reason that's important is because if you don't monitor the status of this, you think you've got a nice, healthy, resilient ring that can survive one break. But I told you earlier, device nets or Ethernet's really good at fixing itself. If I disconnect this, nobody will even notice it unless I'm monitoring it. So if you set up a DLR ring, it's important that you monitor it, or you'll think you have resiliency. Somebody's unplugged a cable and you don't. It's opened up into a linear bus, and the next cable somebody pulls, you're going to have a problem. So it's important in a DLR ring or any kind of device ring to monitor the health of that ring. Most of our Stratus 5700s and 5400s can have DLR direct access. So at least 2 of the ports on the switch can act as a DLR port. These are the switches that can. And one of the last things on a DLR DHCP, in the past, we couldn't set the IP address in a DLR ring, but now with the 5700, it can act as a DHCP server, and assign IP address by position in the ring. So if something's missing, it can get its IP address by knowing which one's missing and giving it the correct IP address. So this is kind of cool, something that no other ring supports this, to my knowledge. There are some advanced protocols for some advanced rings, but it wouldn't timing wise, it wouldn't work within the DLR program. So this is a pretty big deal in industrial networks, is a device can get its IP address by position in the ring. So a drive fails in the middle of the night, you don't have to worry about setting the IP address. You just plug it in there and it'll get it from the server or the switch. And you typically have to turn this feature on. It also supports IGMP snooping, which is a protocol that blocks multicast traffic. I told you earlier, multicast traffic turns a switch back into a hub. So this ring supports the ability to stop that. And that was kind of the presentation. I hit some of the very big highlights of Ethernet, why they do some of the weird things they do. Why we used to tell you a different story than we're probably telling you now is because as networks grow, we have to learn how to adapt and learn how to segment and route our networks properly. And that is a presentation that I put together for some specific customers that I wanted to share with you today.
Thank you, Jeff. That was wonderful. We do not have any live questions in the chat at this time, but for anyone that does have any questions, now is your chance to ask Jeff anything that you would like to know about Ethernet and what was discussed here today. We'll give a few minutes here for anyone that has those follow-up questions. And while we wait, I would like to reiterate that you can reach out to us even after this live stream is ended at macandmaclive@nc-mc.com, that email address there on the screen. If you do reach out to us this way, just be sure to let us know the name of the session in your email, and we'll direct your email to Jeff so he can respond to you. All right, I don't see any questions coming in, but again, feel free to reach out to us at that email address at any time, even if you're watching this as a recording. Thank you, Jeff, for a really wonderful presentation here today. And thank you to Todd for being our resource out in the comments section. And a big thank you to all of our live viewers for your time here today. We had a wonderful group from all over the world with us today, and I really appreciate you joining us here. We hope this session was informative and engaging for you. Remember to subscribe to the McNaughton-McKay YouTube channel for more industry content, and we look forward to seeing you live again soon. Thank you, everyone. Have a great day.